Hello, and welcome to exponential growth and decay rates and compounding interest. It seems like they don't go together, but they're all exponential. It's all good. So let's start with a fact, and the fact is that exponential growth and decay can be modeled by an exponential function where the base multiplier b tells us specific information about the growth or decay. All right, so we'll get to that. So what is this whole growth or decay rate? Our definition is the percentage change in a quantity per 1 unit of time is called the growth or decay rate, R. The relationship between the rate and the base is given by the base equals 1 plus R. Okay, let's see what that means in terms of what we're about to do. Example, a swarm of 120 fruit flies in an experiment grows at a rate of about 9.8% per day. Okay, so we're using exponential functions, and our exponential functions will always be of the form a times b to the x. Okay, and we have our relationship b equals 1 plus r. So a swarm of 120 fruit flies, that will give us our a value. Find an equation for the model of the number of fruit flies in the swarm. So let's go f, I'm going to use a capital F, of x equals 120 fruit flies. It grows at a rate of 9.8% per day. So we know our base will be 1 plus 0.098. Just like when we were working with any rate, any percentage, we have to turn it into a decimal before we can use it in our actual arithmetic, our math, our algebra. Percentages are nice to give us an idea, a nice 0 to 100 scale, but we use the decimal form always to do our work. And let's make that an x, as our x is the number of days. And we know that because the growth rate is given in days. So the number of fruit flies is equal to 120 times 1.098 to the power of x. After 20 days, f of 20 is 120 times 1.098 to the 20th. We'll go over here to the calculator and let the calculator do the work. I'm going to put it in exactly as I see it, 120, parentheses, 1.098. Close the parentheses, raise it to those 20 days. It looks like we will have approximately 778 fruit flies. Let's see if I can spell fruit flies. Not really. Okay. And I didn't round, I rounded mathematically. I'm not rounding in terms of living or any possible moral argument. I'm just using math rounding or common sense rounding in all of my problems. All right, that's it. Don't make it any harder than that. All right. So I'm going to remind us over here. Let's put it in blue. Y equals a times b to the x, and b equals 1 plus r. Okay, and we'll need that as we do all of these examples, so we'll just keep writing it for us. According to the CIA World Factbook 2008, looks like I need some updated examples here. The population of Liberia can be modeled by p of t equals 3.1 times 1.027 to the t, where p of t is the population of Liberia in millions, t years since 2005. All right, so in millions is going to be important, and since 2005. Use this model to estimate the population of Liberia in 2015. What I know is that 2015 should not have a line there. There we go, 2015. If I subtract my start of 2005, I'll end up with, I don't know why, there we go. It's telling me I'm using blue, but it's giving me green. It's kind of weird. A t-value of 10. So in 2015, p of 10 is equal to 3.1 times 1.027 to the 10th power. So I'll use my calculator. I'll let my calculator do all the work. I'm not going to put in parts of it here and parts of it there. I use this Wabbit emulator, which I found free at the Google Play Store. I have it for both my phone and my computer. I'm really sorry, TI, if that infringes on your copyright, but it's out there. I use it. But Desmos.com for all your calculator needs. Desmos also has a nice app. So if you have a small calculator, just a basic calculator that you use in class, at least when you're doing your homework, you could use some of these other tools in order to evaluate it all at once. But as always, make sure you use something appropriate so that you can use it in your classroom as well. I'm going to call that 4.05. I'm going to round to 2 decimal places. But does this mean there's 4 people in Liberia? No, it's the in millions, right? There's about 4 million people in Liberia in 2015. All right. And we could check the books and see if that was true or not. According to this model, what is the growth rate of Liberia's population? What is the growth rate? That's telling me to find R. Well, I know that B equals 1 plus R. I know that my B is 1.027. So I can find my R value and turn it into a percentage. Since this is positive, it will be growth. If we were to find this was a negative value, we would have a decay rate. All right, so 2.7% growth rate is, according to that particular model, population of Liberia in 2015. All right, let's keep going. Let's talk about Madagascar. The gross domestic product, GDP, of Madagascar in 2005 was approximately 16.9 billion US dollars and has grown by a rate of about 6% per year. Remember that the base is always 1 plus the rate. So my base is 1 plus 0.06. That's 1.06. And the gross domestic product in 2005 was 16.9 billion. So what I'm going to do is, for Madagascar, T years since 2005, the GDP of Madagascar will be 16.9. That's how much we had in 2005. 16.9 billion. 1.06, that's our base, found using the growth rate to the power of T. All right, T years since 2005. So this whole answer is part of our answer. So in 2010 is 5 years later. 5 years later, like it's some kind of movie here. M of 5, that's 16.9 times 1.06 to the 5. The gross domestic product of Madagascar in 2010. Let's see. Should have been, if it continued growing at that 6%, should have been about 22.6 billion United States dollars. That's a lot. Why US dollars? Because I live in the States. That's what we use here. If I were in a different country, I would use a different country's money. Okay, keep going. Keep going here. For compounding interest problems, we're going to use the formula A equals P times, parentheses, 1 plus R over N to the NT. A is the future amount. P is the principal amount invested. R is the interest rate as a decimal. T is always time in years. And N is the number of compounding periods per year. So if we have quarterly, we'll end up with N equals 4. If we have monthly, N equals 12. So whatever adverb, right, and then in the ly, you see in the problem, you need to change it into how many of those happen each year. So 4 to the 12. It's a lot like the scaling we did in another lesson with bacteria. Okay, so if 30,000 is invested, let's just start. Let me see. Let's just start underlining things. 30,000 is invested. Tells me that P equals 30,000. In a savings account that pays 4% annual interest, so the rate is 0.04, always as a decimal. Compounded daily, there are 365 days in a year. We don't use the 0.25 here. What will the account balance be after 6 years? And I'm going to underline here too, what will the account balance be? Will be tells me I'm looking for a future value. And that future value is my A. So what we know is that this future value is 30,000 multiplied by 1 plus 0.04 over 365 to the power of 365 times 6. I put in all my parentheses and I'm going to type it into my calculator the exact same way. 30,000 parentheses 1 plus 0.04 divided by 365, close that set of parentheses, raise to a power, make a new set of parentheses, 365 times 6, close that set of parentheses and enter, and we'll find when we let the calculator do all the work that after those 6 years we'll have $38,136.97. For money problems, always round to the nearest cent unless it tells you otherwise. This doesn't tell you how to round, so we'll round to the nearest cent. All right. The number E is an irrational number. E is approximately 2.7182818, and you would think that it starts repeating, but it does not. It's a lot like pi. It's just an irrational number. It's actually, the E is named after Euler. It's Euler's number. One of the best numbers that you find in all of mathematics, and when you take calculus, we kind of explain why that is. Now, when interest is compounded continuously, we use what I call the PERT equation. A equals PE to the RT. The P is still the amount invested. The R is still the rate. The T is still the time in years. A is still future amount. But now this E takes care of our continuous compounding. And I'll talk more about that in future lectures, but not for intermediate algebra. That will come closer to maybe some pre-calculus. I might foreshadow it, but generally calculus is where we talk about what this E is and how we find it. So if that same 3,000 were invested, 30,000. I don't remember what I said. How bad is that? I'm not even listening when I record. 30,000 is invested. We have 4% annual interest. Compounded continuously tells us this formula. After 6 years, we will have P, 30,000 multiplied by E to the 0.04 times 6 in parentheses on our calculator. I'm going to clear that out. I'm going to put in the 30,000. And then here in blue, we see an E to the X. It's above the LN button on our calculator. So since it's in blue, I'm going to press the blue second key before I press LN. Now it's going to put me in an exponent. I'm going to use parentheses anyway because it's just a good habit to be in. 0.04 times 6 R times T. And we'll get $38,137.47. I'm going to scroll a little bit, get two answers on the same page here. Notice we only earned about 50 cents more between daily and continuously because it was only over 6 years. These, after 50 years, they would have very much different answers. Compound interest is really dependent on the long haul, the long term. So we'll get more into that in future lectures. That's it for this one. It's our last example. Thanks for listening.